The I²RiMA paper claims to detect mental stress from EEG signals using spectral Riemannian representations and temporal attention. This is a fascinating intersection of signal processing and machine learning, and I wanted to see if the underlying principles could be practically applied in my lab for real-time biofeedback or even just robust signal classification. EEG signals capture electrical activity from the brain, reflecting different states like alertness or relaxation through distinct frequency bands. Stress, for instance, often correlates with increased beta and gamma activity, while alpha waves might decrease. The challenge isn't just recording these signals, but extracting meaningful, consistent patterns from noisy, high-dimensional data that varies significantly between individuals and even within the same person over time. This variability makes robust classification difficult. The core innovation is using Riemannian geometry to represent EEG data. This handles the complex non-Euclidean nature of brain signal covariance matrices, offering a robust feature space. Traditional machine learning often treats data as points in a flat Euclidean space. However, EEG covariance matrices, which capture how different brain regions interact, don't behave that way. They live on a curved manifold. Riemannian geometry provides the tools to measure distances and perform operations directly on this curved space, preserving the intrinsic structure of the data. This approach can lead to more stable and discriminative features for classification, especially with high-dimensional, time-varying signals. Beyond the spatial representation, the paper integrates temporal attention. This mechanism allows the model to dynamically weigh different time segments of the EEG signal, focusing on the most relevant moments for stress detection. For example, if a stressor causes a brief, intense brainwave shift, the attention mechanism can prioritize that specific window over less informative periods. This is crucial for real-time applications where the onset and duration of stress can vary. So, where does this advanced technique add real leverage, and where might it be overhyped? The mathematical rigor is compelling, but practical deployment faces significant hurdles beyond the lab. Implementing I²RiMA in a personal lab setup means dealing with raw EEG sensor noise, electrode placement variability, and the sheer computational cost of Riemannian operations. While the theoretical gains in classification accuracy are notable, translating that to a robust, user-agnostic system for real-time stress detection is a different challenge. The leverage comes from its potential for highly personalized biofeedback systems, but for general-purpose, off-the-shelf stress detection, the data variability and calibration overhead remain significant hurdles. Exploring these deep technical papers and attempting to replicate their findings in my lab is how we push the boundaries of what's possible. If you're interested in the practical application of advanced signal processing, machine learning, or just seeing what works and what doesn't, subscribe and join the discussion. What other complex papers should I break down next?